We have only 2 more classes after today, and the plan is that we will spend the rest of today looking at the moons on the outer part of the solar system. By next class, we'll make it to Pluto, and then we'll talk about the asteroids and comets a bit on Monday, or Tuesday, I guess. And then the last class, we'll try to put a bow on this whole project that we've been going through. And yeah, that's pretty much it. I think we'll try to do the coffee hour one last time next Thursday, and if you guys want to come hang out and have one last time to go over anything. What else do I want to say? Fill out the course evaluations too. Hopefully, if you have had a problem with anything, you've told me already. But definitely, if you can think of ways to do things, some of these assignments to make them easier, tell me that. If you like the class, tell them that too. The administration likes to hear this stuff. It's good for my life. Let's see, anything else? We're reformatting this class. It's kind of a real administrative nightmare because we're trying to open it up to the GE department, whatever that is, GE College or something like that. So we get more first-year students in here. I think we'll succeed in doing that, but it's going to be a bit different. I think we're going to end up having the lab and the lecture be one class, essentially. And I'm thinking about how to do this. I think next year for the final project, it's going to be a little bit different, more like actually imagining, reviewing one of these bodies in the solar system and then understanding the story that's being told about how it got here, and then also trying to imagine a different story for it. So I want to get people to start generating hypotheses, because it's kind of funny how you can come up through an entire science education. You can actually make it all the way to your PhD, and you've never really had the chance to develop hypotheses before. And I think that's a really strange blank spot in the whole science pipeline. So I want to introduce that. And if you have any ideas about how we could do that better, how we could make that project kind of more engaging, I'd like to hear that stuff too. Anyways, before we make it to the moons, there's been a couple of really cool headlines. So I was trying to impress upon you guys, and I guess I'm going to keep doing it through the end of this class, that this discipline, this is sort of hard maybe for you to appreciate because you're not science majors, but astrophysics, particularly planetary science, is just undergoing this massive revolution right now. It's just completely unprecedented. Well, it's precedented only in hundreds of years past with something like evolution in biology. And the people are really kind of waking up to it. It's really exciting. I saw 2 articles I wanted to share with you guys. The first one, this is from Quanta magazine, which is kind of like leading pop physics magazine. You guys maybe see it on your headline feeds from time to time. This was a really cool article where they essentially discuss, and I recommend you all check this out if you're interested in it, but they're essentially talking about this paradigm shift that we've been talking about. And I think this illustration kind of illustrates it really nicely, about the crumbling line between stars and rogue planets, right? So planets, these big brown dwarfy things, or Jupiters that don't have a solar system. And so people are having to really rethink, like we've been talking about, that fine line between what a star is and what a planet is. And we're going to keep going with that paradigm when we start to understand exactly how stars work next semester. So I hope you guys will join me next semester. In some sense, a lot of the big questions that are probably most exciting go down next semester too, because we start thinking about all those bizarre mysteries like the dark matters and black holes of the universe. What the heck is that all about? And so cosmology, the origin of the universe, these bizarre ideas, we're going to tear those apart next semester. But everything that we've got into here, especially with this fine line between planets and stars, between planets and moons, those paradigms are feeding into cosmology too. So anyways, check out this article. It's not going to tell you anything you haven't heard here, but it's pretty cool to see it, literally coming into print the day after I'm sitting there talking to you guys about this. I think this stuff's happening, and one of the reasons I wanted to even teach this class, this isn't my main job or anything, is because I'm hoping to put together a book about some of these ideas too. And so this lecture is kind of a chance for me to organize my ideas. I try to start off each one of these classes with something like a question about some question, right? And I try to answer, and I don't necessarily know the answer when I start off the lecture, but I get a little bit closer each time. And so I really hope that I'd really like to see some of these evolutionary ideas put into one place, because I think it's definitely happening, but all the people that are working on these are kind of in different places. And so the best thing you get is these PopSci articles like this that occasionally kind of stitch the pieces together and interview a number of different astronomers. Yeah.
It was on Good Morning America this morning.
No kidding.
About finding another galaxy 100 light years away that resembled ours, and they were talking about it on Good Morning America.
And like just like the evolutionary principles, or
not the evolutionary, but finding another solar system.
I see.
That was a lot closer maybe than they thought. I just thought it was funny to hear them.
It always kind of intrigued. I think it like captures the popular imagination a little bit, right? Because I mean, I think this would have been more interesting 100 years ago before we had television and stuff, because all you'd see at night is what's happening overhead, and you'd probably have a lot more questions about it. Especially most people live in cities now, and you can't even see the sky in cities for the most part. So I think the enthusiasm's there, but in terms of stitching it all into a narrative, and honestly, I don't have all the pieces yet either. You know, I tried to kind of like run this down with my wife the other night, and I realized that, you know, the transition, particularly between, I'll show you another article in a second, which ties into this. The transition between Neptunes and super-Earths, and then by extension to Earth-like planets, is becoming more and more apparent. And there was another article that came out this morning. May as well just show that one too. You can check this out. Sophia, you might want to write this one down for your project too. This was in Earth and Sky, which is another astronomy magazine. That one's pretty clear to me, right? There's ample evidence that these Neptunes transition into things that look, you know, maybe not exactly like our planet, but something a bit bigger and maybe slightly less evolved. In terms of how the gas giants fit onto that continuum, I'm still drawing a blank a little bit myself. I don't know. I mean, maybe there's multiple paths. There's this really interesting thing that happens in biology where, you know, maybe I've mentioned this already, but I don't think so. You know, you can have two organisms, right? They both have similar structures. So let's say bugs and birds, right? They both have wings. But birds didn't evolve from bugs, right? That's not the general way of looking at it. When you look back across the genetic record, the tree, right? When you deconstruct the tree of the evolution of these things, it turns out that both bugs and birds developed wings because they both needed to fly, right? And so when we think about evolution, it gets kind of complex because you can converge upon a particular design, you know, for lack of a better word, a particular structural architecture, or you can evolve towards it along a path, right? So all the different birds maybe evolved from something, you know, like dinosaurs, essentially, right? And maybe all the winged bugs evolved from something that there was some ancestral winged bug that first appeared, right? With some proto-wings, maybe it was a glider or something. But there's two paths to that. So there's those two aspects. And when we talk about the evolution of the bodies in our own solar system, you know, these Jupiter-like planets, we call them gas giants. I hope you guys realize by now they're not actually a gas, but the gas giants are very similar to stars in some sense. And so in my mind, that's an interesting evolutionary pathway. You know, maybe they were on their way to becoming stars. Maybe they occur at the same time as our sun in the same system, and the sun scooped up most of the material. And so that's where they came from. There's another possibility, though, too, that those planets, the Neptunes and so forth, so where do the Neptunes come from, right? That's an interesting question, because as far as I can tell, we haven't seen any of these free-floating Neptunes circling one another, but we see a lot of Jupiter ones free-floating, right? So fitting the Neptunes, you know, well, Neptune's evolving down into something more Earth-like is interesting and pretty well defined as a hypothesis. But how do you get a Neptune in the first place is a really interesting question, and the models are really unsatisfactory with that. So do they evolve from something more like a Jupiter, right? Because, of course, we can see differences between our gas giants, Saturn and Jupiter. Are they on a continuum themselves? Are they at different stages of their evolution? or are they something that's formed separately under similar conditions? So anyways, this is just where my head's at with these things, and it's really exciting. So this article that came out this morning reviews an actual scientific piece that came out this week. And they were trying to understand how these super-Earths form from Neptunes. And they have various reasons to believe that they do. And they're trying to explain that radius gap that we talked about. You see these two clusters of these smallish ones, and then you see a gap, and then there's bigger, these sub-Neptunes, smaller Neptunes, but not small enough to be super-Earths. And they were trying on different models for, well, maybe the atmosphere is getting blasted off by stars, and they couldn't really make that work in their models to the extent that it would happen, happen fast enough. Let's say it would take a very long time, even if the Neptune was placed pretty close to the star. And so they proposed a new mechanism, which I hadn't heard of before, which has to do with actually all of the elements at the core, as they become decompressed with losing some of that atmosphere due to the photoevaporation at the star, then they start to radiate. All of their radioactive elements actually start to decay because their circumstances have changed. They're under far less pressure. And so the radiation, so these stars are actually these planets are actually very radioactive. And that radioactivity is actually what's blasting off a lot of the atmosphere in the final stages, which is pretty cool. So these ideas are really on the move. It's just such an exciting time if you're interested in this stuff. I mean, this class is absolutely nothing like what it would have been 10 years ago. I mean, absolutely nothing like it. We would have been telling this Laplacian 1700s story that we've been stuck with for 300 years. And so anyways, I'm really excited about that. I hope you guys can appreciate it. Thoughts, questions about anything? Yeah, go ahead, Dusty.
I was looking at watching the TV on Jupiter, and I was imagining that asteroid belt that's outside of it and how I was thinking like some of the outer planets, if they could have been rogue planets.
The asteroid belt's actually interior to Jupiter, but Jupiter has a bunch of asteroids that it pulls around with it. It's not the belt itself.
Because that's what I was looking at. I was thinking that maybe Jupiter flung the outside planets out there, and that's how they got in line. Because but I was just searching for stuff.
Yeah, I mean, those Neptunes definitely have to have moved, is the thing. There's a problem with forming them out there, which has to do with how heavy they are and how fast they would be moving at that time, and they wouldn't have been able to have stayed. So the thought is that they maybe formed, in some sense, nucleated all this ice out there, and then were dragged in, and then spent some time interior, and then moved back out. There's been a lot of change. This ties into your project, Sophia, too. There's absolutely necessarily been a lot of change in the orbits of the solar system. The question is, why, right? And the best thing anybody can think of, as far as I can tell, is that another star passed by very closely and destabilized things. Of course, there's no trace of that, right? Other than that, we do know that there's something very interesting too, which is that our star doesn't have an obvious companion, and almost every single star that we see has a partner, right? There are two stars orbiting each other, or three, or four, right? Almost all of the other stars seem to have this. So where's ours? What happened? Did that change things radically when we lost our partner, or were we just this strange fluke that didn't ever have a partner? I find that one, I find the odds are that we probably lost that partner at some point. Or it's moving so slowly that we can't detect that we still have a partner. There's various proposals for potential stars that are our partners still. They're just, it's hard to see that motion. So yeah, the orbits absolutely have had to have changed. The question is, did they change very early in the formation processes, or do they change sometimes, right? Remember, the sun passes around the galaxy. It makes a trip over hundreds of millions of years around the entire pinwheel galaxy, and it goes through those arms, right? It doesn't just sit in an arm as the galaxy turns. It moves through each of the arms, which means sometimes it's going to be in really dense areas of stars and star formation, and sometimes it's going to be in those really empty voids in between the arms of the galaxy. And so that has to cause all sorts of different interactions. And whether it's near misses with stars or whether it's just more encounters with radiation and cosmic rays and all of the processes that you would expect from newly formed or dying stars, there's certainly going to be a lot of opportunity for, well, let's not say catastrophe, but for change, right? So that's quite interesting. And of course, that feeds back into what's going on Earth too. Like, if we look at the history of the Earth, it's been a crazy diversity of climates on this planet. Of course, we have this regular 100,000 years-ish cycle where we go through these glacial periods, right, and interglacial periods. We're, of course, in the warm interglacial right now. But beyond that, if you look into the deep history of the Earth, it's been very bizarre in the past. Like when the dinosaurs were here, there weren't any of these glacial, interglacial periods. It was a very different situation as far as climate and weather was concerned. And why is that? Is that because the Earth was evolving? Is that because it was in different parts of its, was it in different parts of the galaxy where it was interacting with its neighbors differently? So we don't know, but those are interesting questions. All right. Can you guys help me remember a bit about what we talked about last time with Io and Europa? So we're making our way through these moons. I wanted to spend 90% of the time on Jupiter's moons because they kind of cover all of the bases. We'll look at Saturn's moons a bit today, and then we'll basically barely touch on Neptune and Uranus, mainly because we've been there the least and we know the least, but also because the same types of moons pop up over and over and over again. And so we don't need to, beat a dead horse. But these two are really interesting. The two that we did make it through last time, Io and Europa. Can you guys help me compare and contrast these things? What do you remember? Yeah, Shane.
Well, Io has just a whole lot of active volcanoes on
Yep.
the surface.
It's probably the biggest difference, yep.
That are able to propel the material out of the atmosphere and provide to Jupiter's magnetic field.
Yeah, that's another really interesting point. So Io is contributing to the magnetic field, which is quite interesting. So it's spewing all of this stuff. Now, Europa, what's going on with Europa? You remember?
It's the smallest moon of Jupiter. It's 100 times the water on it than we have on Earth.
That's really interesting, yeah.
It has a lot of cracks in it, and it has no impact craters, doesn't it? It's the smoothest.
It's very smooth, yeah, which makes it the brightest moon in our solar system too, because it's very reflective. So Europa kind of sets up a platform too that we're going to see over and over again as we keep moving forward, in that it has this icy shell and it's got this subsurface ocean to it. Now, a lot of these things, I've been trying to piece together how exactly do we know what's going on underneath the surface of these things, right? And a lot of those ideas come from very specific analyses of the density versus the radius, right? And they'll do these flybys where they can actually get readouts of the gravity as it changes depending on where you're at in the surface, so they can tell whether it's homogeneous or whether there's a big continent type thing here and there. And of course, in the case of these guys, we actually see these cracks, in some sense in the ice where geysers are spewing out, right? I think we looked at a few of these last time. And so we can measure, we can in some sense taste the material that's being spewed out of these things. And that's how we get the idea about these salty oceans that are down below. And then based on the dynamics of what's actually flinging that material out, we get a sense of how much there is and under what pressures and so forth. And so this theme that we see over and over again is really, really fascinating because these moons have these huge oceans often. They're of course encrusted in ice because it's very cold out there and they don't necessarily have any source of heat. They're all very far from the sun. Remember, way back at the beginning of this course, we looked at why Earth is sort of a magical situation. It's kind of miraculously located, right? It's in this perfect little spot where we get enough radiation to have liquid water on our surface as opposed to a crust of ice like the rest of these guys. But it's not so hot that it's cooking off our ocean, right? So it's in this really beautiful little Goldilocks zone. And these moons don't seem to have that same opportunity, right? They're very cold, and they don't have much internal heating either from radioactive processes. They don't have a lot of heat left over from formation, which is really interesting, and to me points at them being much older than something like ourselves, but it's hard to say. And so we have this huge layer of ice to contend with on these bodies, and we're going to see that more and more as we move through these moons. Any other thoughts on those two guys that we looked at? They're very, very interesting and unique, but they do qualify a sort of type. We don't see anything exactly like Io ever again, except that, well, a lot of the sulfurous processes that give its form, we do see again when we get out into Saturn and so forth, and we'll talk about that. Titan's a really, really interesting moon that's also yellow, but it's much more hazy. It has a bigger atmosphere and so forth, so we'll play with that in a second. But this, the Europa form of moon seems to be really quite common, actually, in our own solar system anyways. All right, and yeah, along those lines, the next moon that we get out to on Jupiter is called Ganymede. This is the largest and most massive of all of the solar system's moons, actually. And you know, in appearance, it's not so different from the last one that we looked at. Not quite as smooth. There's a lot more impact craters on this thing. It's also the only moon that does seem to have a magnetic field, which tells us something about its internal structure, right? It must have some sort of conductive magmatic activity, right? There must be something that leads to the convection currents necessary to actually get that magnetic solenoid type thing going, although we know very, very little about it. Here's a nice little reference with respect to our moon. Actually looks a lot like our moon, quite a bit bigger though. What's kind of interesting about this one, you know, we've talked about how Galileo was the first person to really see these moons. That might not be entirely true. So I came across a report from actually 365 BC from China, where this astronomer actually claimed to have seen this moon of Jupiter, which a moon of Jupiter, and this is the easiest one to see. And this guy's name was Gandhi, maybe? And what's interesting is that he had perceived it as being a kind of reddish color. And I don't know, it's hard for you guys to see on this screen, I apologize. If I turn that light down too much, you won't be able to see me. I won't be able to see anything. But it does have a little bit of a brownish, reddish tint to it, so that's sort of compelling. At any rate, here it is in its orbital resonance. So it's in 4-to-1 with Io and Jupiter and Jupiter. So it's in this 4-to-1 resonance, which means that it's going around 4 times for every 1 turn of Jupiter. And this is a really stable pattern. Of course, this is probably why these moons persist. We talked about this a fair bit before. Now, one thing that's really puzzling is that Ganymede it has a pretty circular path to its orbit, which means there shouldn't be a lot of tidal sloshing going around, right? When we looked at Mercury, we talked about how Mercury has this really eccentric orbit, kind of very elliptical, which means that it kind of, all the material inside kind of crashes to one side like it's on a ship or something, right? And this can heat up the internal materials, but this doesn't seem to be the case, which makes us even more confused about how the thing is able to have a magnetic field. And so the thought is, well, there's a couple of options there. Is there some sort of internal heating due to radioactive decay processes or something like that, which again indicates maybe some youth to it that's not there in the other moons. And the other idea is maybe that magnetic field is just an imprint of some earlier time in its evolution, right? And what that would have been caused by is anybody's speculation at this point. Did it exist in some other location, perhaps with proximity to something that was it closer to Jupiter and got imprinted with Jupiter? It has a pretty strong magnetic field. Was it close to the star? We don't know. So, very interesting puzzle there. All right, what else do we want to say about this thing? Like I said, okay, so we didn't mention this, but it does also seem to have evidence of a subsurface ocean, just like the last one we were talking about. This is because we get this Galileo satellite, which was a mission, let's see, not sure when that one was launched, I don't have it written down. But a recent spacecraft that traveled out there was able to actually taste some of these compounds that were in its immediate vicinity and get a sense of what was happening down underneath the ice. And it seems like it's a very salty, let's see, magnesium sulfate, sodium sulfate, all sorts of stuff. Carbon dioxide, sulfur dioxide, cyanogens, hydrogen sulfate, basically a bunch of really interesting and certain organic compounds, which is, of course, intriguing because organic compounds are just the chemicals that life needs in order to build itself. And so, again, big hopes there that if we punch down into this subsurface ocean, we might find something prebiotic and give ourselves, some, as soon as we find something that is even approximating biology, right, we're going to have a much better idea of how this whole thing got started here on Earth. Or even if it did get started on Earth. I mean, one thing that's going to be really, really fascinating is if, let's say, we find some bacteria or something on one of these moons. Well, you know, the immediate assumption is that, well, their genes would be very, very different than the bacteria that we find here on Earth. But what if they're not? What if their bacteria look basically the same as bacteria here? In some sense, I don't think that would be too surprising, but I think it would be shocking to the scientific community. It would also make a real mess in terms of trying to understand origins of life on Earth, because at that point, you don't know whether it came from somewhere else or whether it actually arose here on Earth independently. Because it might be, again, a convergent situation like I talked about at the beginning of class. Do organisms everywhere originate very simply from protocells and so forth, and they come up with the same solution to the problem every time? They always come up with these DNA codes, they always come up with the basic cellular floor plan, and they essentially solve the same problem because they're facing the same circumstances. Or are they evolved in a chain from one another? Are they passed from planet to planet over time? There's been some really intriguing, we'll talk more about this next semester, but there's been some really intriguing results where people look at the spectra, right, the light coming from different nebula, clouds of material very far away, and they see organic compounds. And in some sense, they see the spectra that approximates that of actual cells itself, right? So there's been some interesting reports where the spectra of something like E. coli is very closely replicated in some of these clouds. Now, does that mean there's cells in those clouds? There's no way to really know. It could be just that they're full of the same chemicals as cells, right? But certainly, there's always been this lingering thought that life may come from somewhere else and not just from under our feet. And in some sense, that kicks the can down the road. And it starts to tie into the cosmological questions, like, does the universe have a beginning or not, right? And if it doesn't, well, maybe it's just always been a feature, right? Just like atoms, maybe life have always been a feature of the universe. And I think trying to wrap your head around the idea of the universe not having a beginning is very hard for most people, which is why I think that people are clinging really desperately to this Big Bang hypothesis, which is, it's taking a lot of heat right now, and we'll talk more about that next semester. But it puts you in a whole new conceptual realm if you think about extending the time frame for all of these, especially if you think about unbounding the time frame, right? If the universe doesn't actually have a beginning, if it's just kind of always been here and always will be here, well, that's a really long time to make things happen. And anyways, we're gonna get closer to some of these questions very soon when we start drilling down into these planets, or moons, I suppose. By the way, the line between moon and planet is an interesting one. Of course, we define it sort of arbitrarily, like moons are essentially little planets that orbit planets, right? They don't orbit a star directly, but something like Mercury in appearance is very, very similar to something like this, right? Or there's actually ones that we'll look at that are even closer to Mercury. Our moon, for instance, looks a lot like Mercury, although Mercury seems to have a much more active inside than our moon. But that might be just because it's warmer and it's sloshing around a lot more. But they're not necessarily really different types of bodies. And so if we can put Mercury on a continuum evolutionarily with respect to something like, say, Mars or the Earth, then we're getting closer to unifying all of these bodies under an interesting framework. So remember, the standing model is that these moons formed at the same time, more or less, well, let's say shortly after Jupiter was formed at the beginning of the solar system. But in some sense, this kind of beggars belief because they're very, very, they're very diverse. Some of them appear to be much older than others. And just the idea that you would accrete these very dense rocks together in orbit by themselves around these huge giant planets is very perplexing to the imagination. It really strains the imagination. So change is a coming. All right, so what do we want to say about Ganymede? We've already said that. Let's take a look at we've already talked about its internal structure, but let's have a little picture. The thing that we have at the inside of this thing is not too different than our own planet. Of course, the ocean is much, much bigger. Of course, this body, this moon, is much, much smaller than the Earth, right? But the basic differentiation, rocky-ish mantle, iron sulfide liquid core, right? That's the only reason we imagine that is because we need that magnetic field to come about somehow. And then it's got this iron-rich inner core, which stabilizes that magnetic field. So it's very different, right? It's very strange how different it is than the other moons in some sense, right? All of these moons are very, very different around Jupiter. And so the idea that they kind of happened at the same time, it's a very difficult picture for me to wrap my own head around. But if they've been scooped up over time, if they've had lives in different places, that might explain some of the features a bit more. And maybe they've had lives, I'm going to just go completely heretically out on the line here, but if this thing maybe spent some time billions and billions and billions of years ago in the past as something more like an Earth-like planet, or something more like probably not as an Earth-like, because it has way more water still than us, but maybe something like a Neptune, right? And this was originally the core of that, right? And then that would make a bit more sense how you actually get all of this heat and compression going on at the insert. And then it was just scooped up by Jupiter, maybe billions of years ago, maybe a long time ago still. But maybe it had a history that predated Jupiter itself. It's an intriguing idea. Here's a look at its magnetic field. Not that I want to say anything else about that. Generates its own aurora, which is interesting. It has a very tenuous atmosphere, which is oxygen-rich in some sense. That's quite interesting. Quite a bit of O3, so ozone, which is generated by interacting with UV light from the sun, presumably. So there is a mission that was just launched this year called the JUICE mission, which is pretty hilarious. Jupiter Icy Moon Explorer. I don't know how they get juice out of that, but they call it the JUICE mission. And this is the planned path. It's kind of interesting. They're basically going to go and circle around Jupiter, which we see over here for a while, and kind of narrow down their orbits on that. And the reason they do this is because it's a lot cheaper on energy, right, on fuel, to get involved to take advantage of the gravitational system and actually join in the gravitational system and then slowly nudge your spacecraft into new orbits. And then eventually they're going to make their way over to Ganymede and actually start orbiting it itself. And they're not going to actually put any kind of a drilling device down this time around, but what they are going to do is at the very end of this project, I'm not going to say crash, but they're going to land the spacecraft on the surface to the best of their ability and hopefully get some, data from the surface, let's put it that way. Maybe some pictures, maybe they're obviously not going to return any samples, but they'll maybe be able to taste the surface a bit, and depending on where they land, maybe they'll get a closer look at what's going on underneath it too, depending on how good that data turns out to be. So that'll be really cool, and that was just launched. Now, that's going to take a long, long time. So it's going to take, let's see, it left this year. It's not going to reach Jupiter until 2031, right? It's a long ways away. And then it's going to do a bunch of these gravity assists to get to where its target is. And so it's going to enter orbit around Ganymede in 34. And then that final impact is supposed to happen in 35. So I think we'll all live to see this happen. Fingers crossed. And it'll be really interesting how this story updates. So I hope you guys will keep that in mind many years after you've stopped thinking about planets. Maybe you'll keep up with it. All right, and then the furthest of these Galilean moons is called Callisto. And you might remember Callisto comes from that myth of the bear that we talked about. There's a really rich history there. I just can't overemphasize enough how significant it is that we still peg our mythology to these bodies as we name them. All right, so this is the third largest moon in the solar system. It is just after Ganymede and Saturn's largest moon, which is Titan. Actually, people thought Titan was the biggest moon for a long time, but it turns out it's just its atmosphere. So, I don't know, it depends how you draw the line. But so we have this, the third largest moon. It's very, very comparable in size to Mercury, but it's much less massive. So it's almost exactly the same diameter, but it's less dense. It's only about a third as massive as Mercury, which is interesting. What else can we say about it? This is actually the one that people are thinking about as a potential target for setting up a base to explore all the other moons in the future, because it's far enough away from Jupiter that it's not going to be subject to the magnetosphere, so the trapping of all those high energy particles from the sun. It's not going to be essentially in that radiation belt that's really nasty. So it would be a good place to set up camp and then maybe do robotic explorations of the more dangerous surfaces as you move closer towards Jupiter. Let's look at it. There it is next to our moon. This thing, by the way, is incredibly cratered, right? It actually has so many craters that there's craters covering every single crater to the extent that we can't even possibly put a date on this thing based on cratering. It would just be gazillions of years old. And I don't think that's insignificant either. I think that's really fascinating that these dating ideas are. I mean, dating is one of the hardest things you could possibly try to do, and we have this very high precision dating method that's quite reliable to a point, right? So this radiometric dating is really, really good for telling you the last time that a rock formed, right? But it can't really do anything beyond that. So this thing looks really old. Let's leave it at that. Again, seems to have this very common salty ocean right beneath its kind of outer icy crust. And because of the fact that it has no magnetic core, it has no appreciable magnetic field, we don't think that there's anything sloshing around inside of it in the rocky world, any of these metals are liquid or anything like that. So it's thought to be sort of geologically dead, much like our own moon. Which kind of makes sense if it's really, really old, too. Now, I don't think that, like Batygin's model that I showed you guys the video of last time, I don't think that it would have this thing being that old, but it certainly looks much, much older than everybody else, for whatever that's worth. All right. Yeah, so some of these craters, I don't know if you can see this one very big. This is essentially, you see these rings around this thing? This crater essentially is like taking up a good half of the planet, right? So this thing must have gotten slammed by something that was more than 100 kilometers across, right? Much bigger than the Chicxulub, the one that ended the dinosaurs, let's put it that way. Although I did see a really interesting article this week, little tangent about the Chicxulub crater that, in addition to, so when I was a kid, people didn't know whether it was a meteor that slammed into the earth that killed the dinosaurs or whether it was just a period of intense volcanism. And this paper that just came out argues that it was a little bit of both, actually, that the impact from the Chicxulub meteor set off a bunch of volcanism all around the world, which contributed to that kind of, long period of overcast, sort of cloudy, terrible weather that essentially killed off the plants, which killed off the big megafauna that depended on the little guys eating the plants and so forth, this big chain reaction of doom. So maybe a little bit of both. But as you can imagine, whatever hit this thing Well, first of all, it hit it a long time ago because this crater is covered in tons of other craters. And by the way, it's not like we see lots of meteors striking these things today, right? It's very, very rare that you'll see a meteor strike even the moon, our moon, which is very easy to see in close up. But we don't see that happening. So these don't seem to accumulate very fast unless there was some very interesting catastrophe in the deep past, right? Again, if the solar system interacted with another solar system, for instance, maybe that would dislodge asteroids from the asteroid belt. Maybe it would dislodge things from the outer Oort cloud. These things are very difficult to get a grip on. So, you know, you don't really know whether these impacts accumulate over time very continually or whether they happen kind of all at once. But they couldn't have happened all at once because there's multiple layers of them here, and they all seem to have different agings. But certainly this thing's been through the mill, right? It's been beat up pretty bad in the past, but it's recovered. So while this impact is like, maybe this asteroid was only slightly larger than the one that took out our dinosaurs, the planet's tiny compared to our planet, right? So it would have been much more devastating. You can imagine that this thing would have just been completely remodeled, you know? Much the same as that, I think I showed you guys some simulations of the Thean impact that people think formed our own moon. And it basically liquefied the planet, right? If you see these simulations, you see these two bodies basically merge together, and it kind of spits out the other side almost, right? It's like you get two planets that make two brand new planets almost as a result of it. And I have my reservations about that hypothesis too. It's very perplexing to me why the Earth would have maintained all of, let's say, all of the atmosphere and water, and the moon got none of it and stuff like that. I'm not totally sold on that idea, but it is the sort of prevailing popular one at the moment for whatever reason. At any rate, the point is this thing would have been completely slaughtered by an impact like that, and it would have changed everything. So maybe it looked a lot different in the past, and we just don't know that. There's also some big dreams about terraforming this thing, which I thought I'd mention. You know, the big problem, the big draw, of course, is that it's in a safe location with respect to Jupiter. The big problem is it doesn't seem to have a lot of heat. You know, there's let's see. The basic ingredients that we would need for life are, of course, there. We have plenty of water and salt and organic compounds and the things that we love. But we also like to stay warm, right? And so it's not entirely clear how that would happen. Now, if you think back to when we were talking about Mars, I think I mentioned briefly that there's this idea that maybe generating an artificial magnetic field isn't such a big deal after all. In other words, you can have a satellite, some sort of, you know, let's say nuclear-powered satellite that's basically setting up a magnetic field, and it orbits the planet and creates that deflection. You don't need that much, because remember, these particles that you're trying to shield yourself from, these solar wind, they're really light. They're like the lightest elements you can imagine, essentially, right? They're mostly just, they're ionized hydrogens and heliums and so forth. So you don't need that strong of a magnet. You do need it to be diffuse and ever present, essentially, but maybe you can set that up in orbit. So anyways, people are hatching dreams about this, and we'll see what happens. I think that people will need to explore terraforming concepts, but you know, it's going to be a bit of an arms race. Like maybe we can, every day I feel like there's a new article about a new Earth-like world that's being discovered. I think we've discovered hundreds of them at this point, and some of them aren't that far away, right? So it's like, well, we learn how to terraform some of these dead-ish looking landscapes before we find a way to actually get out to these other star systems. I don't know, it'll be an interesting race to see which we get to first. All right. I think that's going to cover our bases for Jupiter. Let's check out Saturn, because Saturn is very singular and beautiful. Has anybody had a chance to see Saturn with binoculars or a telescope or anything like that? So Saturn's actually, right at the moment this year, it's actually facing, the rings are kind of head-on, so you can't see them too well. Now you got to think Saturn has an axial tilt just like the Earth, so it has seasons, but Saturn's orbit is much, much slower than the Earth. So from year to year, it's in a different position with respect to what we can see. And so last year, it was tilted a bit towards us in such a way that we could actually see the rings really beautifully. You could see them with binoculars and with a telescope, and it was really quite magnificent. Right now, if you go and see Saturn, it's going to be tilted towards us, and you can't really see the rings, unfortunately. But they're there, and we just got done with this beautiful Cassini mission, which went out there and took some incredible pictures, which, I mean, a big part of what I'm going to do for the next few minutes is just show you some incredible images of these things, because they're just some of the most magnificent images I think that we've gotten from the solar system. And it's very puzzling. This ring system is a huge open mystery, right, in terms of well, is it being, in some sense, we have evidence that it's being generated still, in some sense, by the outflow of material from some of these moons, right? We're going to talk about Enceladus. Enceladus has geysers, just like we talked about on Europa, but the geysers are actually giving off enough material that it's building its own ring around itself, which is really, really fascinating. But some of the rings appear to be potentially aggregating new moons inside of them. There's little asteroidy looking things that we call them moons, but they're basically on the scale of asteroids, small asteroids, and they're accumulating new stuff on them as they go around, so they're like little seeds. And there's other cases where those asteroids are coming apart and making rings. And so the question about this ring structure, the questions are sort of unending. It's like, is this a process, or is this the remnants of a moon, a bigger moon that fell apart and is now reorganizing itself with all of this dust? And so there's no hard answers on that. I think that some of the more popular ideas right now are that indeed the ring system as a whole, the majority of it, came from the destruction of one of its moons, which is really interesting. But on the other hand, most of those models that we saw, like we watched, I keep referring to this video that we watched I think it was last time, that Batygin did down at Caltech. And as you may have noticed, Jupiter also was organized in a ring structure according to these models, right? It started off as something like a nebula, a disk, but that progressed through a ring-like structure. And of course, the standard models for solar system formation all start off with ring-like structures too, that eventually lead to the accumulation of these planets and so forth. So, you know, it's like a chicken or egg question, which came first, and we don't know. We really don't know, but we can at least say some things about what we see. So here's a bunch of the little tiny moons that we talked about. Again, they don't really look much like moons. Most of them don't have sufficient mass to be shaped into spheres themselves, right? They're just sort of these, you know, highly rough and broken asteroid-looking objects. Gaps too, right? The ring structures have these various gaps in them. Now, when we see gaps in protoplanetary systems, in these exosystems, we see some stars that have rings around them, right? This has been a wonderful new feature that we've gotten from the James Webb and from the Hubble before that. We see a few star systems that have these rings around them as well, and we think those, well, the hypothesis is that fits into the nebular disk model for how these solar systems form. But what's interesting is in those models, you see these gaps in the rings open up, and the reason the gaps open up in the standard model for solar system formation is because the planets are scooping out the holes in them. However, that doesn't seem to always be the case. So there are some gaps that are opened up by moons that are crossing by, but other ones, not so much. There's nothing there, which is really, really strange. So was there something there that got destroyed? And if so, why didn't it leave a debris trail, or did it join in with the other rings? We don't really know. It's quite interesting. Now, the rings, just like planets, seem like they could be involved in resonance with one another too, and that might stabilize some paths versus others. And that seems to be the case for certain rings, like the Titan ringlet and the G ring. This is also really interesting too. I don't think that you guys can see this, but that little dot off to the, not the inset picture of Saturn, that little dot off to the left there is this is a blown up version of that. So Saturn and its main rings is at the center here, And there's this huge diffuse ring structure even further out, which is tilted at 27 degrees. So it's a bigger ring structure than it appears to be. This big diffuse one is called the Phoebe ring, which there's a moon out there called Phoebe, and it's thought to be, in some sense, associated with Phoebe. So it's much bigger than the ring structure is much bigger than just this beautiful ring, these rings that we're going to mostly fixate on. Let's see what else. We talked about the seasonal tilt and how that makes it pretty nice to see. It looks like we're going to get a nice ring plane crossing where it'll be tilted towards us. That's going to happen again in 2025. So mark your calendars. The next one's not going to be till 2038, so you definitely want to catch it in that window. There's going to be another one, 2039, two of them in 2039. Full planar, as much of a tilt as you can possibly hope for. But 2025, March 23rd, check it out. All right, so let's take a look at some of these. So what are the rings made out of? They're mostly made out of water ice, which is really quite interesting. Now, we know that a lot of these moons have a tremendous amount of water in them, right? And so I think this feeds into the hypothesis that these rings resulted from the destruction of a moon, perhaps, that was out there. There's some other stuff involved, too. There's a little bit of organic material in them, these tholins. There's silicates, too, so pieces of rock. But those are really just impurities compared to the main mass of these materials. And by the way, all of the particles are very small, but not that small. Some of them are on the boulder size. So some of the particles that you see in these rings are on the order, they're up to 10 meters in size. All right. Let's take another look. Again, some of these banding structures that you see, what's kind of interesting is that while these particles are kind of water ice, they seem to have, the rings actually have a little bit of an atmosphere themselves, which is almost entirely oxygen. It's very, very thin, though. I think if you took all of that oxygen and smushed it down so it was in the plane of the ring, it would be like one atom thick. So a very small amount. And this is basically due to that water ice interacting with the ultraviolet radiation that's splitting up the water, essentially. It's a hydrolysis reaction. All right. What else do I want to say about this? Yeah, this moon, this idea that it's a broken up moon is very old. It was proposed by Edouard Roche in the 19th century, and it was kind of abandoned for a while. Like I said, the alternative hypothesis being that it's just part of the original nebula from which Saturn formed. The idea was actually recently resurrected, and I think that people are more and more considering the idea that the rings are younger than the formation of Saturn itself, which is, I think, reasonable. The problem is that these water ices and so forth don't last that long. So in the absence of a method of continually regenerating them, we wouldn't expect them to persist that much longer. In fact, I think most scientists don't expect for these rings to be around for that much longer than your or my lifetime. But on the order of 100 million years, something like that. So if they're only going to last that long, then they couldn't have been here much longer than that in the first place either. And so this has reopened the idea that there was a moon impact. Or this illustration kind of shows it to you too. The moons, right, are subject to all sorts of gravitational pressures themselves. This is something we haven't even talked about. But it's possible that a planet or a moon could just be ripped apart, right? Because it's being tugged around under extraordinary force. I mean, you can imagine swinging your hand around your head. Let's say you kind of feel at some point the blood's going to build up in your hand, right? And there's a lot of pressure there. And if you swing it hard enough, it might be possible to destroy it in some sense, or at least shatter and sling off all of the water which would, of course, form ice very quickly without the insulation of that protective shell. So that's another possibility. All right. Oh, this is a very, very beautiful picture. This is the Keeler Gap, and this is one of Saturn's tiniest little moons called Daphnis. And this feeds into the bigger solar system formation model, right? Because in this sense, you actually have a moon that's cutting out a little channel in the rings, right? And this is what people think when they see solar systems forming with rings and discrete bands in them. They think, oh, well, there must be a planet in those gaps that's scooping it out. And it does seem to be the case with something like Daphnis in the Saturn ring system. But some of the other rings don't have that, like I said. So it's not a totalizing mechanism. It doesn't necessarily account for all of the bandings that we see. And that's still a mystery. So, I think this is going to feed into all these mysteries that I keep throwing at your feet. I think what we'll try to do next year, in so much as you're interested, is I think that the final project will be more focused on trying to propose a potential solution to some of these problems. And I don't expect people to have, genius ideas, but I do think that there's tons of possibilities you can imagine for how these things happen. And so I'd love to see what people come up with on their own. All right, you can see those interesting swaths being carved out. This is Prometheus, which is another little moonlet, which is carving out this beautiful kind of spoked-like pattern in one of the F rings.
Is that where it's changing its orbit a little bit?
It's just sort of like sweeping through it like this, yeah. It's kind of corkscrewing through it, I believe.
Oh, okay, it's wrapping.
I think so, yeah.
Okay.
Yeah. Pretty incredible. And it's probably tumbling too. So. All right, so we have some fairly appreciable moons, right? We're going to talk about Enceladus, which is pretty tiny, but it's very, very interesting. And we're going to talk about Titan, which is outside of this scale. Now, these other moons that we don't really have time to get into them, but needless to say, they kind of fit into the patterns that we've already seen so far. Titan and Enceladus are particularly interesting. Titan is very strange. We'll look at it in a second. And Enceladus is very, very similar in some sense to something like Europa with these geysers, right? Except we've had the opportunity to actually check out some of these geysers, and they're very intriguing. It's at a safe distance from Saturn II, so we might be able to actually explore it a little bit more. And again, hope for being able to taste some signs of something approximating either life or something prebiotic, right? Something before life. Because the question becomes, again, if life is something that arises out of non-living material, what does that mean? What does that look like? How's that possible? Because it kind of goes against every principle of biology that we have otherwise. So maybe we'll get some signs of something that's not quite life, but maybe on its way to becoming so. All right. So there's Titan, by the way. Absolutely enormous. They thought this was the biggest moon in the solar system because actually its atmosphere is so enormous. And in one of these recent missions, we had the opportunity to do this kind of radar imaging of the surface, at which point we realized that it was smaller than we thought it was. That was very, very recently. And then Enceladus is kind of a minor moon, also very smooth, icy surface, and we'll talk about both of these guys in detail in just a second. By the way, in terms of where all of the material is in this moon system, this is a comparison of the different moons' contribution to the overall mass. Titan makes up almost all of it, right? So Titan is appropriately named for the giants of the Greek mythology. It's enormous. So let's look at this thing. Now, it's thought that Titan's primarily composed of ice and rocky material, which is similar to some of the other guys we've looked at so far. But it has this very, very strange yellow atmosphere. It's also, which we'll talk about the composition of that, but what's even more interesting is that when the Cassini mission went by, I think this was in 2004, they did these laser imaging of the surface, kind of similar to how we image the surface of Venus, right, underneath all of these clouds. And what they found is that it's covered in these lakes of liquid hydrocarbons. Now, that might not seem that unique or interesting to you, but it is, because it's the only other place besides Earth where we see liquids on the surface of a body. That's very, very unique and strange. What's even more funny is that prior to 2004, oil, all of the oil, right, that we would have, that we have on our planet, they used to call it fossil fuels, right? I think some people sort of stick with this anachronisms to this day, but it was really funny because as soon as they discovered this on Titan back in 2004, they abruptly stopped calling they stopped calling hydrocarbons fossil fuels here on Earth, because it was very apparent that all of a sudden these lakes on Titan were not formed by decaying dinosaurs and so forth, right? And decaying plant matter is probably a more reasonable way to look at it. Now, certainly some of our hydrocarbons on Earth are formed that way. Coal is a great example. But there seems to be abiotic, so non-life-based ways of generating oil. And this was an absolutely revolutionary discovery at the time, because the prevailing thought was, hey guys, and a lot of the climate, well, it wasn't called climate narrative back then, but let's say the environmentalist movement was something like, well, we can't keep using this oil because we can't make more fossils, something like that. That's probably an oversimplification. I don't mean to insult their reasoning or anything. But that argument didn't really make sense anymore, right? Because we understood that oils actually come from other processes besides decaying organic matter. And so let's take a look at some of those. Those lakes are really, really, really something to see. I'm going to skip over Christian Huygens for now. Here's a good comparison with respect to our own moon. Just such a strange-looking planet. So before we can get down past the atmosphere, by the way, let's talk about that atmosphere a little bit, and then we'll look at the lakes. So the atmosphere is actually, in some sense, very, very similar. It's actually mostly nitrogen, just like ours, which is quite interesting. Now, it's also at the same, it's a little bit denser than our atmosphere, but it's on the same order of density. It's something like 1.2 times. 97% nitrogen with 2% methane, a bit of hydrogen, and trace amounts of other gases. So all of this methane is getting smashed by radiation from the sun, and it's resulting in this kind of smog, right? This is like very similar to the way LA used to look when I was a kid. They've cleaned that up significantly. But it's the same sort of smoggy process that's driving that. And, it's interesting because the idea is that the energy from the sun should have basically converted all of the methane from Titan's atmosphere into very complex hydrocarbons over the course of like a few tens of millions of years. So the thought is that there must be some way that Titan keeps replenishing its atmosphere. And we don't know how that happens exactly. I think we'll go over a couple of mechanisms here if we have time. But let's, there's probably some sort of volcanism that we're not aware of, some sort of seepage from the interior. And how is that methane, how are those hydrocarbons being generated in the first place? Is it in the absence of decaying organic matter? Is a really interesting question. Skip this. I want to show these lakes because we're going to run out of time. So this is a map of the surface, and I'm not sure why this image has darts in it. I guess they just didn't have good data for those portions. But you can see these lakes. They look very similar to the lakes on Earth, but they're basically just oil, right? There's just these like tar fields essentially, but it's liquid methane as opposed to more complex hydrocarbons. Liquid methane, yeah. Here's a close-up of one of those. All right. A few more. There's also this really interesting dune-like feature that they saw on the surface. Now, the dunes are not necessarily thought to be generated in the same way as our dunes here. So the sand is not made up of tiny little silicates like it is here on Earth. It's actually thought to have formed when it's not necessarily like these dunes are scooped up by the winds, perhaps. The sand are laid out by the winds like they are on Earth. The idea here is that the liquid methane actually causes a kind of rain that then gets caught into the various weather systems on the moon itself and results in this erosion, which presents these. On the top, by the way, I have this is Earth. And down here we have on the bottom, yeah. Sorry, we don't have such good pictures of the surface. But down here you can see a similar banding structure. But these are still hypotheses. People don't really know. There's also this there's the presence of these tholins, which are organic molecules that are traditionally associated with life here on Earth. They're biotic in nature. But the idea is that there could be photochemical reactions in the atmosphere that led to the precipitation of these tholins, which then leads to some of this banding structure in combination with the winds. So very, very, very little known about these things, but very intriguing because we don't see these dune-like structures on anything else. So what's causing that? We don't totally know. We also don't have any nice methane rainstorms here on Earth, right? Or methane lakes. I mean, it's really nothing we can compare it to other than our own precipitation systems. So very little is known. Now, this is the only picture that we have from the surface of this thing. So Huygens was this atmospheric probe. It actually touched down on Titan, but it only managed to survive there for a few minutes. Let's see, 90 minutes it lasted after touchdown. Not sure, I didn't have a chance to look into what went wrong, but you can imagine almost anything can go wrong when you're 6-8 years away from Earth, and just very difficult to communicate and navigate and all of those things. So what did they see? I mean, there's not much you can pick out of this picture is the unfortunate truth. Evidence of erosion. There was the claim of some sort of river system. I'm not seeing it in this picture, but I guess somebody sees it. Yeah, they probably just nerd out on it and try to, exactly. The interior of it. Again, very typical interior, right? Like most of our other moons that we've looked at, subsurface ocean. I mean, and this, of course, has to do with the elements that we see coming out of it. Now, it also, these are very speculative, though, right? I mean, until we were actually able to get over there and do more tests, it's very difficult to say anything. That's what makes kind of taking this tour through the back half of the solar system very, very difficult for me, because I don't want to tell you these things with any serious degree of certainty, because a lot of these are just formulations based on density and atmospheric traces and how did these different compounds end up on the surface and so forth. We don't really know. So anyways, it's something to keep an eye on. I think we'll continue to investigate Titan. I want to make sure that we save a little bit of time for Enceladus before we close out the day. There's the hope also that, so people have also toyed with the idea that life could, you may have heard, well, is it possible that instead of carbon-based life forms, we have silicon-based life forms or something, right? And so there's a community of astrobiologists that are desperately hoping that we might see something like methanogenic life forms on something like this, right? There's liquid methane. Is there a life form that is able to, construct itself from those ingredients and able to exist inside of this methane-rich environment? And I don't know. It's just it's a hope, but exactly. Yeah. So could methane serve as the solvent? I'm skeptical of that, but we'll see. I mean, the reason I'm skeptical is because water is just such a unrivaled molecule. It really just can do things nobody else can do. There's something about the shape of water, and it has that positively charged regions, two of them. It has the negatively charged regions, right? So it can build structures. It can It can participate in hydrating all the proteins in your body. It does a lot of work that's unsung in the textbooks of biology, right? We're learning more and more about how important and unique water is to life. So I don't know, maybe. You never say never. We're always shocked by what we find. So, okay, let's take the last few minutes to check out Enceladus, because Enceladus is a very promising, it's most promising for this region. So this is a picture taken from Cassini, and you see all these lovely geysers spewing forth from it. These are these cryovolcanoes, right? They contain water vapor, molecular hydrogen, some solid materials, sodium chloride. So far, NASA has identified 100 of these geysers. Some of them are raining back snow. Some of the material escapes, and like I said, it's building up that E-ring of Saturn, which is really interesting. But it's absolutely evidence that there's a subsurface ocean, particularly at the South Pole, with liquid water in it. And this is in some sense manageable. So the ice on top is not 100 kilometers thick like in some of the other cases we've looked at. It's much more manageable. I actually failed to write down the thickness of the crust, the icy crust on the outside of this. Maybe I'll find it later. But it's much more manageable. So the thought is that we actually have a chance of maybe penetrating this crust and getting a closer look at this. And again, if Enceladus is characteristic of all the other moons of the same subsurface phenotype, then maybe we'll be able to study it more easily than the others, and we'll be able to make these sort of inductive statements about the other moons. Look at it. It's really, really tiny compared to our own moon, actually, right? So this, in some sense, makes it easy to work with. It's going to be easy to land and leave from. There's not much gravity on this thing. What else can we say about it? Okay, this is the ring that it's creating with its geysers, by the way. This is the E-ring, named for Enceladus. So the E-ring is, again, this is a great example of how the rings could be self-sustaining, right? And maybe some of those rings that we don't know, that we can't make sense of, maybe they were created by moons similar to Enceladus that sort of just burned themselves out, let's say. Right? Maybe they lived and died, and all they left behind were their rings. Maybe not even that long ago. That's a possibility. Because this ring shouldn't sustain itself for more than another million years or so. Right? It just wouldn't hang around that long. These volatile, tiny little particles, these waters and ices, right? They're just going to be gone. They'll dissipate. They'll be destroyed by radiation and so forth. So it's a self-sustaining ring system. All right. And again, no magnetic field, so the thing's thought to be essentially dead inside, much like our own moon. And there you have it. You have this icy crust, and then you got that subsurface ocean. If we said that the subsurface ocean's like 10 kilometers deep, well, then it looks to me like the outer crust is only a few kilometers thick, which makes it quite manageable. I mean, that's quite a hole to drill, but if we talked about some of those cooking methods that we thought of in terms of getting through, it seems like we could be able to accomplish that in a reasonable amount of time. All right. So Cassini went by and actually tasted this atmosphere. I think we talked about that a little bit. Now, what do I want to say about that? The internal heating is a bit interesting. So they found this. When they look at the heat map of the surface that it has these weird tiger stripes of heating on it, and they can't really make sense of that. Just to throw another mystery in your lap, it doesn't seem like the amount of heating that we get out of the thing is like 10 times higher than you would expect just from radioactive decay of the interior of it. So either it has more molten stuff, in other words, this thing is much younger than we thought it was, or some other mechanisms going on. And people haven't really been able to figure that out. There's not a lot of this tidal sloshing that could account for it. So where's all this heat coming from, and why does it appear with this strange banding structure? That's a really good question, and I don't know that anybody has the answers to that. More work to be done, my friends. What else can we say? All right, I think that that about covers it. So we have our work cut out for us in terms of the places that we want to visit. Of course, Jupiter is going to be our best candidate. It's close-ish. It's still a few years away from us, so it's not easy. But if we can learn some things up close, if we can set up that base way out in a safe place, maybe on Cassini, we can explore those other moons. Maybe what we learned there we can transfer to our knowledge about Saturn. And maybe we can hop our way out towards the edges of the solar system to the point that we're actually capable of starting to go and find ourselves a backup hard drive for this planet. So next class, we will talk about Jupiter very briefly. Jupiter is part of a big family of objects now called trans-Neptune objects, and that'll feed nicely into asteroids and comets, which will close out the tour of the solar system, and we will wrap it all up on our final class. Otherwise, good luck with the rest of your classes. I hope the semester is working out well for everybody, and come see me if you have questions.